All right, guys, we are looking at simplifying rational expressions. Ariel! Ugh. All right, talking about simplifying rational expressions. So if you have paid attention to some of the vocabulary that I've shared with you, rational, right? In our first lesson, I said that when you think of the word rational, you should be thinking fraction, okay? And what made something a rational function? It was an expression that involved variables, right? Well, what I want to do today is I want to simplify rational expressions. So what that means, if you think about putting those words together, it means, well, we know what simplifying means. It typically means to reduce something, right? Or make something that is complex into something less complex. Would we agree with that, right? So simplifying rational expressions means we're going to take fractions that have variables in them and we're going to make them look nicer, right? We're going to reduce them, okay? Well, in order to do that, let's start with something that you guys are familiar with. 18 over 12. If I asked you guys to reduce that fraction, you would go through this process in your mind. I think you would, at least. What is a factor of 12? And you would say, okay, well, 2, 3, 4, and 6. And you would ask yourself, well, do any of those go into 18 evenly? And if so, what is the biggest one that goes into 18 evenly? 6 does, right? And so in your mind, you would divide 18 by 6, and you would write 3. And you would divide 12 by 6, and you would write 2. Agreed? Well, why am I allowed to divide those both by 6? Because if I divide the top by 6 and I divide the bottom by 6, I divided them by the same thing, right? And why is that okay in math? Because 6 divided by 6 equals what? 1. So it doesn't change the value of the expression, does it? Right? And that's kind of what we did here. Taking 18 over 12 is the same as 3 times 6, which is 18, and 2 times 6, which is 12. The 6 is reduced to give me a 1, which is why 18 twelfths can be reduced to 3 halves, right? So that's sort of the thought process that you go through and that you were taught years ago. So how does it work when I throw some variables in there, right? How does it work when I throw some variables in there? Well, here I have a fraction, and it's now a rational expression because I have the what? The variables in there as well, right? So I'm a little bit more specific. And when you decided on 6 in that previous problem, right? When we chose 6, give me a phrase for 6. What was 6? Greatest common factor. It was the GCF, wasn't it? Okay. Now, would 2 have been a number that worked? But it wouldn't have been the greatest common factor. So what you're really going to do here, guys, is this. You're going to look at this whole expression. And you're going to look at this whole expression. And you're going to ask yourself, what's the greatest common factor? Well, has to be a 3. Has to be x to the 5th. Why not x to the 8th? Why not x to the 8th? Why would I choose x to the 5th over x to the 8th? Yeah, for a GCF, I have to pick the variable that has the smallest exponent, right? And then I have y to the 6th, and I have y third. So which one am I going to take? The y to the 3rd, right? So my GCF is 3x to the 5th y cubed, which leaves a y cubed. 3x to the 5th y cubed, which leaves a 2x to the 3rd. These things reduce, and I'm left with that. So let's do, I'm going to come back to this one in a minute. So flip the page for a minute. So I want to simplify each of these, okay? So really what I want you guys to do, is I want you to find the GCF of the top and the bottom. So right off the bat, I got a 4 and a 20. Which one of those two do I got to take? The 4. And why is 4 okay? Because it goes into 20, right? Then I have an x squared and an x to the 10th. Which one of those am I going to take? The x squared. And then I have a y to the 8th. Does the other one have a y to the 8th? So I'm not going to take that, right? I'm not going to take that. So what I'm going to do is I'm now going to take this fraction and I'm going to write 4x squared over 4x squared, right? And I'm going to ask myself, what do I need to multiply 4x squared by to go back to this? Well, 4 times what gives me 20? A 5. And x squared times what gives me x to the 10th? X squared times what gives me x to the 10th? Not x to the 5th, x to the 8th. Because what do I do when I add x, or when I'm multiplying? I add the exponents. Good. And then what's left? A y to the 8th. Okay, so I have the top. What about the bottom? What do I have to multiply 4x squared by to get 4x squared? 1. So there you have it, guys. And now what's my last step? And it seems kind of weird, but what's my last step? To reduce the 4x squareds. So what's left? 5x to the 8 and y to the 8. That's really what you're doing, right? Let's look at the one next to it here. Guys, well, let me do this. Let me do it this way. Hang on, and then I'll play the other game. 7 and 21. GCF. 7. X cubed x to the 5th. Which one am I going to take? Y and y to the 8th. Which one am I going to take? All right, so I'm going to write that on the top and the bottom. Okay, what do I have to multiply 6x cubed y by to get 6x cubed y? 1. And 7 times what is 21? 3. And if I have an x to the 3rd, what do I need to get an x to the 5th? X squared. And if I have a y, what do I need to get a y to the 8th? A y to the 7th. And so my last step is to reduce the common factor. And this is the reduced form. Okay, is that all right, guys? Right? I actually like, when I do these and I'm reducing these variables, I like to play the where's there more game. You remember that phrase, where's there more? Did I do this with you? Okay, good. So, guys, I have x's on the top and x's on the bottom, right? Where are there more? On the bottom. How many more? 2 more. I have y's on the top and y's on the bottom. Where are there more? On the bottom. How many more? Y to the 7. And then what did I do? I took 7 over 21 and reduced it to 1/3, right? So if I look at this problem and I use the same set of questions, 20 divided by 4 gives me 5. I have x's on the top and x's on the bottom. Where are there more? The top, how many more? 8. I have y to the 8th and y and no y's. Where are there more? On the top, how many more? 8. So we leave it like that, right? So I actually like that process as well, okay? But if somebody was to ask you to show your work, this is a way that you could show it, right? I'm taking a GCF out. Everybody okay with that? Questions? All right, so if I flip back for a minute, what makes this second example different? Well, here's how I want you to determine which method you're going to use, because there are two methods to do this. If I look at this first example that we did, guys, and listen to the question carefully, how many terms are up top? Now, I heard 2. What separates a term from another term? So if I said x squared plus 3, how many terms? If I said x squared plus 3x minus 8, how many terms? If I said 4x, how many terms? So how many terms are up top? 1. 1. Because what separates terms? Adding and subtracting. 1 term up top. How many terms below? 1. Anytime you have 1 term divided by 1 term, you're playing this game that I just showed you guys. Anytime you have any other scenario, 1 term over 2, 2 terms over 1, 2 terms over 3, 3 terms over 2, any other scenario, you're going to go to this second method, right? You're going to go to the second method. And here's what the second method involves. So how many terms did I have up top? 2. How many on the bottom? 2. Anytime you have more than 1 in either position, you're going to factor and reduce. Now, if you think about it, I sort of did a factor and reduce technique earlier. It's just a weird kind of factoring, but I did. Okay. So, factor and reduce. Guys, x squared minus 9. Why do you think we spent all that time working on factoring? Because I need you to recognize x squared minus 9 immediately and right away as the difference of perfect squares. So what does this reduce to be? X plus 3 times x minus 3. 2x plus 6 has a GCF of 2. Leaves x plus 3. What do you notice about the top and the bottom? They both have a what? They both have a common factor. So factor and reduce. The reduce means to simplify common factors. The reduce means to simplify common factors. And what does simplify common factors means? It means any factor that is the same as a factor on the bottom can be reduced to 1. Now I wrote this, guys, in two steps. This is how I factored it. I could rewrite it like this, right? And then what's anything divided by itself? 1. So what does that leave? X minus 3 over 2. Fair enough? Okay. Now I don't really require you guys to do this step. You can go right from here to here. Okay. It's just what's left over after I what? Cancel, right? After I cancel the common factors. All right, so let's do a couple of examples of these. I'll come back up to 9 in a minute, okay? So, example A, how many terms in the numerator? 3. How many terms in the denominator? So this is a factor and reduce. So, if I have 3 terms, what kind of a problem is that? How do I factor that? Set them, set them equal to 0. Not going to set, what you're trying to do is find them, right? So what am I trying to find? 2 numbers that multiply to be negative 14 and add to be 5. Good. What are the numbers? Multiply to be negative 14, add to be 5. Close. Other way around. Positive 7, negative 2. Why positive 7, guys? Because I need to get a positive 5, which means the 7 has to be positive and the 2 negative, right? Cool. You're going to immediately identify the bottom. The bottom is a DPS. x plus 2, x minus 2. And so my question now is, are there any factors that are the same? So can I reduce them? Absolutely. Now, when I reduce them, what do they really reduce to be? Well, we saw it on the previous example, 1. Now, we could write 1 over 1. Okay? In fact, it's a good habit to do that. You'll see why in a few minutes. Okay? What's left? X plus 7 over x plus 2. Now, do I really need to write the times 1? No. Okay? I'm going to alleviate a lot of confusion. Okay? And this is how I determine those that really pay attention and those that don't. Okay? I want to talk about the difference between. So this is my final solution, by the way, okay? I want to talk about the difference between this versus this. Okay? Let's talk about the difference. What are you tempted to want to do when you got to this point? What are you tempted to want to do? Go ahead. You could, if you thought this, if you thought there was something else you could do, what was it? Again, I want you to remind yourself of what the directions are. The directions are to simplify or reduce. Okay, so you always say like the next step, but I like what you're saying. You're saying, I think, what I'm suggesting. Is anybody looking at this and wondering why you can't do that? Anybody? Raise your hand if you thought that or if you considered that. Good. Let's talk about why you can't do that. Let's talk about why you can't do that. Let's suppose for a minute that x equaled 3. If x equaled 3, what's the top of this fraction? Don't write this. You don't need to write this down. Just watch. If x equaled 3, what's the top of the fraction? 10. What's the bottom of the fraction? 5. So what do I get? 2. Well, if your assertion is right, that I'm allowed to do this, then I should get the same answer as what I got right there. But what's 7 divided by 2? 3.5. It's not equal to 2, is it? No. Okay. So there's one reason. Okay. By the way, let's do the same example here. What's 7 times 3? What's 2 times 3? 6. What does 21 divided by 6 reduce to be? 3 halves. So would I be allowed to cross out those x's? Oh, sorry, hang on, not 3 halves, but I give you guys the wrong number. 7 halves, right? Because I can reduce both of these by what? 3. 7 halves equals 7 halves. So does this seem like you would be allowed to cross those x's out? Seems like it, right? Seems like it. So let's use the phrases that I've been suggesting to you guys. Ready? Here's where it's all going to come together. How many terms are in the top? How many terms are in the bottom? So your directions are to factor and reduce. But the top's already factored. And the bottom's already factored. And are these factors the same? No. So I'm done. Look here. How many terms in the top? How many terms in the bottom? 1. When I have 1 term in the top and 1 term in the bottom, I'm supposed to see if they have a GCF. What's the GCF of 7x and 2x? X. The x's can be reduced. You see the difference between the two now, okay? So in this scenario, you cannot cross out the x's. In this scenario, you can, okay? 4x squared minus 1. That's a DPS, difference of perfect squares. 2x plus 1, 2x minus 1. What about the denominator? What can I take out of the denominator? A 5. And what does that leave? 2x minus 1. Any factors common to the numerator and denominator? What's left? 2x plus 1 over 5. Done. C. How many terms on the top? 4. What does that indicate that you're probably going to need to do? Grouping. Factoring by grouping. What is a number that I can take, or not a number, but what's the greatest common factor that I can take out of the first two terms? X squared. And when I take out an x squared from these two terms, what's left? X minus 3. All right, we always keep the sign that's between the groups. What can I take out of 6x minus 18? A 6. And when I divide 6 out of 6x minus 18, I'm left with x minus 3. And then what's my last step when I factor by grouping? I look at the two groups and I take the thing that is the same, the x minus 3. And then in the other set of parentheses, I write down all the stuff that's left over when I get rid of the x minus 3. So what's the leftovers? X squared plus 6. Over. Okay, cool. What about the denominator? Definitely another difference of perfect squares, right? An x plus 3 and an x minus 3. Anything common? The x minus 3s. What's left? X squared plus 6 over x plus 3. And you're going to be tempted to keep going. So you're going to look at the top and you're going to ask yourself, how many factors? I'm sorry, how many terms? 2. How many terms in the bottom? 2. Can I factor the top? Mo says yes. What would you factor the top into? There's only 2 terms, right? It's not a trinomial. So there's nothing I can do. Can I factor the bottom? I'm done. Let's go up to 9. Go up to 9. So I'm going to do this one with you guys as a where is there more, okay? Instead of a GCF, just a different way to think about it. The 10 and the 15. Can I reduce that fraction anyway? 10 over 15, what does it reduce to be? 2/3. Very good. I have x's on the top and I have x's on the bottom. Where are there more? On the top. How many more? 4 more. I have y's on the top and y's on the bottom. Where are there more? On the bottom. How many more? And there's your answer. 2x to the 4th, 3y to the 3rd. Now, why did I play that as a where is there more game? Because how many terms were in the top and the bottom? 1, right? All right, so I would imagine that most of us are sitting here and thinking to themselves, well, as long as I can factor, this seems like it's a pretty reasonable topic, right? As long as I can factor, it seems like a pretty reasonable topic. In fact, the next 2 lessons after this are going to have the same theme. As long as I can factor, it'll be a pretty reasonable topic. There is one thing that could mess you up. And it's one special circumstance that you have to consider. And it's actually not a really big thing, but let's talk about it. What's 9 minus 6? 3. What's 6 minus 9? Negative 3. What does that give you? A negative 1, right? What's 3 minus 15? What's 15 minus 3? What does that give you? Negative 1. So does anybody want to venture a guess as to what a minus b divided by b minus a is? Negative 1. Because what did I do? I took the two things that I was subtracting and I flipped them and put them on the bottom of a fraction, right? Well, that is the one thing that could trip you up in this whole mess. And I'm going to use this example to show you what I mean. How many terms in the top? How many in the bottom? So our directions are to factor and reduce. What can I take out of the top? Which leaves? I know that the bottom looks a little weird, but it's still a DPS problem. It doesn't matter if x's are in front or numbers are in front, right? What is 25 minus x squared going to factor into? It's one of these. Careful! 5 plus x and 5 minus x. The order matters. If the 25's in front, hello? If the 25's in front, the 5's got to be in front. If the x squared's at the end, the x has got to be at the end. Okay, the order matters, okay? Now, when I ask you guys, are there any terms that are the same? Your response is no. There isn't. I have an x minus 5. I have a 5 plus x. They're not even the same sign. I have an x minus 5. I have a 5 minus x. Oh, it's the same sign. It's just that the two terms are flipped. And what did I say? X minus 5 divided by 5 minus x gives you negative 1. Now, I'm going to reduce them. And I'm going to get a negative 1. Here's a really important point. Where does the negative 1 go? Does it go on the top? Does it go on the bottom? Does it go both? Does it go top? Does it go bottom? Does it go both? Well, here's the reason why it definitely doesn't go both. Because if it goes in the top and the bottom, what's negative 1 divided by negative 1? Positive 1. So if I put it in both spots, it didn't reduce to be negative 1, it reduced to be positive 1. Here's the answer. You can put it in the top or the bottom. You just can't put it both, okay? So in this case, I'm going to put it on the top. So it's negative 1 on the top. So what do I have left? I have negative 2 over 5 plus x. Is there a choice that says negative 2 over 5 plus x? No, but there's a choice that says negative 2 over x plus 5. And isn't 5 plus x exactly the same as x plus 5? Yeah, with addition, the order doesn't matter, does it? With subtraction, it does. Okay? So choice 1. And we see how this could definitely mess us up, right? And we see how we can make mistakes here. X squared minus 6x plus 9 is going to be a factorable item because there are 3 terms. Two numbers that multiply to be 9 that add to be negative 6 are negative 3 and negative 3. And I can take a 6 out of the bottom, which leaves me with a 3 minus x. So anything exactly the same in the top and the bottom. Not exactly the same, but I have an x minus 3 and I have a 3 minus x. And so I can reduce them. And they reduce to give me a -1. Did I tell you where it goes? I didn't. I'll put it on top. Now, what is somebody going to be tempted to want to do? Also cross this one out. But in order to cross this one out, I'd have to have 1 to cross it out with. And things don't cross out more than once, right? Things cancel and that's the end of them, right? So what's left? I have -1 times x minus 3 over 6. Is that a choice? No, because what does it look like the person did? Distributed the negative. So if you distribute the negative, you get -x plus 3 over 6. And unfortunately, that's not a choice, because what did I say you can do with an addition problem? You can take these two things and what? Switch them, right? So I could make it 3 minus x over 6, which is that one. Leonardo's trying to let that marinate right there. He hated what I just did. But guys, what is -2 plus 3? What is -2 plus 3? 1. What is 3 minus 2? 1. Right? All I did is just switch them, right? Because it was an addition problem. Okay, cool.